Hi, welcome to this episode of ProofPilot. We are finally here to talk about manifolds. Uh, Manifolds require some specific properties, and we have discussed some of them in previous videos. And there is another property that we will discuss that, and then we can get to what a topological manifold actually is. So by definition, a topological space M is said to be locally Euclidean of dimension n if every point of M has a neighborhood in M that is homeomorphic to an open subset of Rn. What actually that means is that let's suppose that this is your space. Okay, if this is your space, then if you take each point, okay, this be an arbitrary point in your space, and then take an open neighborhood of it, then this thing right here should be homeomorphic to something that is a subset of Rn. Okay, if you can find this neighborhood, then we say that this is a locally Euclidean, this space is locally Euclidean of dimension n. Before we proceed, I want to point out a fact that will come in handy in the following definition and following lemmas. Uh, it's the fact that an open ball that is a subset of Rn is actually homeomorphic to the whole Euclidean space. Okay, it's homomorphic to Rn itself. And just remember what a we need to just find a homeomorphism between these two spaces, and this is the homeomorphism we need. Okay, this is my homeomorphism function, which is defined like this, and the inverse of it would be this, and you can just verify that this is actually bijective and both of these things are continuous. And if you want a visualization, if this is the whole space, you can just kind of push all this space into just an open ball. Then we have this lemma, and we will understand why I just stated this fact right here. The lemma is about this definition that we just gave, the locally Euclidean of dimension n. We just want to verify some facts. I'm going just to read the lemma. A topological space M is locally Euclidean of dimension n if and only if either of the following properties holds. Okay, every point of M, which was your space, has a neighborhood homeomorphic to an open ball in Rn, or every point of M has a neighborhood homeomorphic to Rn. Well, if you're going to prove this way of the lemma, I mean, if you have these facts and want to confirm that M is locally Euclidean, that will be just satisfied by the definition of a locally Euclidean space. And another thing that I want to point out is that these two things are actually the same statement. Why is that? Because an open ball in Rn is homeomorphic to Rn. And why is that true? I just stated them that there is a homeomorphism. I gave you the homeomorphic function. And that's it. These two statements just are equal. So I just want to show that if my space is locally Euclidean of dimension n, then these two things holds. And I'm just going to prove this, the first statement, because these two are equal. So the way I'm going to prove that is So M is a locally Euclidean space. And I'm going to prove that there actually exists, for each point, there actually exists a neighborhood homeomorphic to an open ball in Rn. So we just need to find that neighborhood. So because M is locally Euclidean, then it means that for each point, let's take your point as P, then there exists a homeomorphic function from the neighborhood around P to an open subset in Rn, which I'm going to call U, and this U is an open subset of Rn. Okay, so this is an open subset of Rn. And another fact that we know about open subsets in Rn that we can actually uh, find an open ball in this neighborhood. So I'm going to say that open ball is B, and then if you just take the inverse of your homomorphism from that open ball, then you get a neighborhood in your space that is homeomorphic to an open ball. So that I just found the neighborhood itself. So this statement right here is now proved. Now we are ready to give the definition of what an n-dimensional topological manifold is. An n-dimensional topological manifold is a second countable Hausdorff space that is locally Euclidean of dimension n. That's just the definition of a topological manifold. In simple terms, if you take a neighborhood and that neighborhood looks like the Euclidean space, the space that we work with every day, then you can say that that's a topological manifold. But there are some confusion in the definition, and we need to rule them out. Okay, these are non-examples that show that these things right here are not manifolds. Why are they not manifolds? We all know what this shape is. We have encountered this many times. Just take this point right here. As you can see, this thing right here does not have that neighborhood that we are talking about, or the union of an x-axis and a y-axis also does not have that neighborhood that we needed to be a manifold or to be locally Euclidean. Why is that? Well, you may say that we can say that this thing right here looks like R1. Okay, I can just take this neighborhood. Well, that's the problem with the definition. It should not bring any ambiguous claims from other observers. I mean, if you are taking a neighborhood, you have to take the whole neighborhood itself. You cannot do this. If you are taking a neighborhood at the origin, that would be your neighborhood, okay? It contains both x-axis and y-axis. And if you go above the origin, you can see that you can just take from either x-axis or y-axis. So that's the problem with the definition, and we just want to rule out some inappropriate claims from manifolds. And obvious examples of manifolds will be the unit ball or the Euclidean space itself. And there are some other examples, but we are not just prepared for them yet. We will see other examples as soon as we investigated some other topological properties, and we will soon get familiar with them. Thanks for watching. If you had any problems with manifolds, I will gladly answer to them in the comment section, and do not forget to hit the subscribe button.